Hi everyone, in this video I would like to review quickly the standard transfer function that we have for a different type of filter, and then I will solve some examples. Let's start with low pass filter. For a low pass filter, the transfer function has this form: k multiplied by cutoff frequency divided by s plus omega c, or the cutoff frequency. So if you have a transfer function in this form, then what you have here, the constant in denominator will be your cutoff frequency, and based on this number you can calculate the gain of your filter. The next filter is a high pass filter. A high pass filter has a transfer function as k multiplied by s divided by s plus omega c. So as you can see, the polynomial in denominator of both of them are first order. The difference is that for low pass filter you have a constant number in numerator, and for high pass filter you have a coefficient of s. Now let's go to band pass filter and band reject filters. For both of them, the denominators are s squared plus beta s plus omega naught squared. The difference is in numerator. In the numerator of a bandpass filter, we have k multiplied by beta s, and in numerator of a band reject filter, we have k multiplied by s squared plus omega naught squared. So as you can see, s squared plus a constant is what we have for a band reject filter, and a constant a coefficient multiplied by s is what we have for band pass filter. Okay, now let's look at this example that I'm going to solve, and let's see how we can decide what type of filter that we are dealing with. So this is the first example. In this example, I want to see if I apply a voltage of VI to the circuit, and by looking at the voltage of resistor, what type of filter I'm going to have. So the first thing that I have to do is that I have to find the transfer function, and then I have to look at the transfer function and see how the transfer function looks like and which transfer function can be a good match for my answer. So what I need is VO over VI, and in order to do that, I'm going to write a voltage divider. So I'm looking for the voltage of resistor. So in numerator, I'm going to have R, and in denominator, I need to have R plus LS in parallel with 1 over CS. Okay, let's simplify this part. LS in parallel with CS means that I have to multiply LS by 1 over CS, and in denominator, I have to add them together. So LS plus 1 over CS. Okay, let's simplify everything. I need to get rid of this CS in denominator, so I'm going to multiply everything, both numerator and denominator, by CS. If I multiply the numerator, then it means that this term will cancel out. In denominator, I'm going to have C here and S squared, and this will cancel out. So I'm going to rewrite my transfer function here. So H of S will be R over R plus LS divided by LC S squared plus 1. Now, what I'm going to do is that I'm going to multiply both numerator and denominator by this term to get rid of this fraction here. So I'm going to have R multiplied by LC S squared plus 1 divided by R multiplied by LC S squared plus 1 plus LS. Now, here I can see that in denominator I have a second order polynomial. So it tells me that this is a bandpass or band reject filter. And in numerator I have s squared. So my conclusion here is that this is a band reject filter. Now, in order to see what is the center frequency and what is the beta for this particular circuit, I need to make sure that what I have here is in a standard form, which means the coefficient of s squared is equal to 1. So what I have here as coefficient of s squared right now is RLC. So I have to divide everything by this RLC, and then I can match what I have with the standard transfer function for band reject filter. So after simplifying this transfer function, this is what I'm going to have. And now that it's the time to divide everything by this RLC. So if I divide everything by RLC, I'm going to have s squared plus 1 over LC, because R will be cancelled out by the R that I have here, divided by s squared plus, I have S here, and then I'm going to have 1 over RC, because this time L will be cancelled out, and finally plus RLC divided by RLC, which is going to be 1. So, sorry, I made a mistake here. So here what I have is only R. I don't have L and C. So consequently, what I'm going to have here is going to be 1 over LC. Okay, now this is my transfer function, which is in a standard form. So obviously this is a band reject filter, and for this particular filter, what I have as constant in denominator is my omega naught squared. So omega naught squared is 1 over LC, and what I have as the coefficient of S is my beta. So my beta or bandwidth is equal to 1 over RC. Knowing what is omega naught and what is beta, I can find the rest of them. Now, in the same circuit that we discussed in this example, if you focus on the voltage across these parallel impedances, so if you focus on this voltage, then instead of a band reject filter, you're going to have a band pass filter. And if you do the calculation, you're going to see that omega naught and beta are going to be exactly the same. The only difference is that it's going to be a band pass instead of a band reject. So omega naught squared will be 1 over LC, and beta will be equal to 1 over RC. So I leave this part for you to solve, so you can redo the calculation, and you're going to see that if you choose the voltage across these elements as your VO, then instead of having a band reject filter, you're going to have a band pass filter. In second example, we have this circuit, and we're applying VI here, and we would like to look at the voltage of resistor as our output voltage and see what type of filter we are looking at and what are the parameters of the filter. So these are what we are looking for. What is the transfer function? What is the filter type? And what is the cutoff frequency? And what is the gain of this particular filter? Okay, so what I have to do first in order to evaluate this filter and see what type of filter I have to find is that I need to find the transfer function. The transfer, obviously, in order to find the transfer function here, I need to do a voltage divider. So before doing that, let me remind you that for the inductor, I need to describe this by its impedance, which is going to be 0.05 S. Okay, now I'm ready to do the voltage divider. So VO over VI is going to be 1200 divided by 300 plus 1200 plus 0.05 s, which is going to be 1200 divided by 0.05 s plus 1500. Okay, so I have the transfer function, and obviously this transfer function is a low-pass filter because in the denominator I have a first order polynomial and in numerator I have a constant. Because of that, I can conclude here that I'm looking at a low-pass filter. But in order to find the parameter of this filter, so this is, I know what is my h of s, I know what is my filter type, but in order to find the cutoff frequency, I have to make it looks like the standard form of low pass filter. So let's see how I can do that. I need to get rid of the coefficient of s, so I have to multiply everything by 20. So if I multiply everything by 20, I'm gonna have h of s equal to, in numerator I'm gonna have 24,000, and in denominator I'm gonna have s plus 30,000. Okay, so now this is in standard form, which means what I have here is cutoff frequency. So my cutoff frequency is equal to 30,000. And what I have in numerator is k multiplied by cutoff frequency. So it's telling me that k multiplied by 30,000 is equal to 24,000. So it means that the gain here is equal to 0.8. So these are the parameter of this particular filter. Okay, let's look at another example. In this example, we're applying Vi here, and again, we're looking at the voltage of the resistor as output voltage. So the first step, what I'm going to do is that I'm going to describe everything by their impedances. So here I'm going to use 0.04 multiplied by s to apply the milli, and what I need to use instead of 40 nanofarad is 1 over cs, which is going to be 10 to 9 because of the nano, and then over 40 s. Okay, now let's do the transfer function. For h of s, I need to describe VO over Vi. So again, another voltage divider, which is going to be 180 divided by 20 plus 180 plus 0.04 s plus 10 to 9 over 40s. What I'm going to do now is that I'm going to multiply everything by 25s, both in numerator and denominator. Why 25s? S because I want to get rid of this s here, and 25 because I want to get rid of the coefficient of s here. So I'm doing this at the same time. So what I'm going to have is h of s equal to 180 multiplied by 25s divided by s squared plus 5,000 s plus 25 multiplied by 10 to 8 divided by 4. So now that what I have here now is the standard form for a band pass filter. So my first conclusion here is that here I'm looking at a band pass filter. Why? Because I have a second order in polynomial, and in numerator I have a coefficient of s and not s squared. Okay, so what I have here is my beta. What I have here is my omega naught squared. And what I have as the coefficient of s in numerator is k multiplied by beta. So it tells me that my beta is equal to 5,000. My omega naught is equal to 5 divided by 2 multiplied by 10 to the 4, which is going to be 25,000. And finally, my k will be 180 multiplied by 25, the coefficient of numerator, divided by my beta, which is 5,000. So k would be equal to 0.9. As you can see, because we are focusing on passive filter, the maximum gain that you can have is k equal to 1, so the gain cannot exceed 1 for a passive filter. If at this point you're calculating a k which is greater than 1, then it shows you that you are doing something wrong in your solution. Now that I have my beta, my omega naught, and my gain, I should be able to calculate omega C1, omega C2, and quality factor.